So let's begin. One of the great ideas of the 19th century is something that has disappeared without a trace, the idea of an ether. When James Clerk Maxwell began to explore electricity and magnetism, he discovered that there could be waves. And of course, it seemed obvious to him that a wave had to be a wave in something. You could have a wave in water or a wave on your jump rope. You could have a shock wave, like the pressure of my voice as it moves through the air. You could kick a desk and feel the shock wave go through that. You could have waves of spinning electrons. You have all sorts of waves, but they're always waves in something. And so it seemed obvious to Maxwell and everybody else that there must be a substance where these electric waves were disturbances in. And so they began to explore what might the properties of that all-pervasive substance be. If light was just a wave, then there must be a disturbance in this medium. Couldn't just be on the Earth, because light from stars came from far beyond the air. So what were its properties? That became a big issue. One of the great American physicists, in fact, the first to win a Nobel Prize, was Albert Michelson. And he, with his colleague Morley, began to explore what our motion in this all-pervasive ether might be. And so he thought, I'll figure out a way of figuring out whether we're moving fast in this direction or slow in that direction, or is the ether moving different sides when we're in different parts of the orbit around the sun. What's going on? And he built the most fantastically accurate device to explore whether we're moving in the ether by sending a light wave in two different directions, reflecting it off mirrors, and then letting the light waves interfere when they got back. It was an extraordinarily sensitive device, and he got no result. He thought, this is the greatest failure of my life. I mean, it's a failure that led to the first Nobel Prize in the United States, but he thought it was a great failure. He couldn't find motion through the ether. Well, one of the great, indeed one of the first, truly towering figures in theoretical physics was the Dutchman Hendrik Lorentz. And he explained Michelson's failure to detect movement in the ether by supposing, just supposing, that every object as it moved through the ether contracted just a little bit by a factor of 1 over the square root of 1 minus v squared over c squared, where v is just the fraction of the speed of light, so v over c is a half if you're going half the speed of light. So you take this factor, 1 over the square root of 1 minus v squared over c squared, and you imagine that for some reason having to do with the way the constituent particles of a ruler or a chair or a house, if you're moving through the ether, you squish just a little bit. And that keeps it from being visible that you're moving through the ether. You might have thought it would take longer to go into the ether wind than perpendicular to it, but no, everything squishes out just enough to compensate for it, and no detection of motion through the ether could be made. And so Michelson was explained. The great mathematician Henri Poincaré agreed. Now, Poincaré was, in addition to being one of France's great mathematicians, the country where you can get your name inscribed in stone towering over the city of Paris by being a great mathematician. It's a country that values its mathematicians. He was a physicist and contributed importantly to physics. He was a philosopher whose books continue to be read even today and were smash hits at the time they were written. He was in charge of the Academy of Letters as well as the Academy of Sciences. He was an extraordinary polymath whose skills ranged from matters of state to the details of some of the most erudite and complicated parts of science. But he began his scientific work as a student at the École Polytechnique, then, back in the late 19th century and still now, a school that prepared people jointly for roles in the state, in the military, in industry, and in science. He recorded everything with an eye towards mapping. And this was Poincaré's great insight into so many branches of mathematics and physics. He looked for ways to visualize things, to map them, to get control of them through our intuitions about the visual world. He wrote to his mother, for example, and drew a picture of the path he was taking in his exploration looking for coal up in Scandinavia. When he got sick, he graphed the shape of the side of his cheek as a function of time. When he went down as a young apprentice to mine inspection to try to figure out how to make coal mines safer and to figure out what happened should something go wrong, he did an extraordinary investigation of one devastating accident which killed many, many miners. And he tracked, by graphing the flow of air through the whole mine, he tracked back where the source of the explosion must have been to a single pickaxe hit on a Davy lamp, a lamp whose small perforations allowed light to come out but kept dangerous methane gas from combusting. He figured out ways beyond these practical matters of coal mining to graph planetary orbits. In fact, we call the Poincaré map an imaginary plane where we see a puncture each time a planet goes through, and then we can look at the pattern of these puncture lines. Are they converging? Are they diverging? What are they doing? And so you take this incredibly complicated three-dimensional problem and reduce it just to a sequence on a plane, a map. And in fact, this Poincaré map led him, after a great deal of difficulty, to discover what becomes chaos theory, nonlinear dynamics, one of the tremendous developments of 20th century science.